So in section 5.2, we are going to define our integral and begin our kind of discussions on that. But I said it's just building off of what we've been talking about with the sums and the approximations from the previous couple of videos and from section 5.1. So here's our definition. If a function is defined on a closed interval AB, the definite integral of f from a to b is the number blah, 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 provided that this limit exists. If it does exist, we say that f is integrable on a to b. So if you'll notice, what we have here is pretty much exactly what we were writing down before when we were finding the areas of the rectangles and stuff like that, right? So a couple of things about terminology. When we have this symbol, whatever the function is, this is what we call the integrand. Okay. This number is the upper limit. And then the a down here is the lower limit. And for now, this piece just tells us what variable we're going to be integrating over. So the dx just tells us we're integrating with respect to x. If it's a dy, we'd be integrating with respect to y. It's what our variable is for our integration. Okay? So if x is integrable on AB, then we have the definite integral from a to b is equal to the limit as n approaches infinity of the sum of I equals 1 to n of x, f of x sub I delta x, where delta x is b minus a over n, and x sub I is a plus I delta x. So picture-wise, this is the same picture we had earlier. If we have some function, and we look at limits from a to b, we have to decide how many intervals, right? So that's what the n is, the number of intervals. And then once we pick that and we set up our little rectangles in here, then of course the delta x is the width of each rectangle. Okay, so that's the delta x, is the base of the rectangle. And then we pick some sample point in here, you know, the x sub I. That's our sample point, and then that's where we draw the height of the rectangle. We evaluate the function at that point and give us the height of that rectangle. And this down here is just telling us we have to do it for each interval. So when we go over 1 delta x, we're in this first interval. If we go 2 delta x's, we're in the second one. If we do 3, we're in the third one, and so forth and so on. Okay, so let's just practice kind of going back and forth in between this sum thing and the notations for the integral. So all you've got to keep in mind is this little piece in here, in between the sum and the delta x. That is the function, okay? So we're going to have here x times natural log of 1 plus x squared. Okay. Now, the interval that you're integrating over, those give you your lower and upper limits, okay, or bounds. I think that's what usually we call them, bounds. Okay. So the lower bound is 2 and the upper bound is 6. And then the delta x there actually tells us again what our interval or our variable is. So we're going to put a dx. Okay. So here's one going backwards. We have integral and we want to express it as a sum. So we're going to have the limit as n approaches infinity. The sum of I equals 1 to n. Okay. Now we take the function sine of 5x, and we're going to tack on the little sub I, because we have to do that, for each interval. And then we put the delta x on the end of it, and there is our sum. Okay. So you do kind of want to be able to go back and forth so you can read some of these things. Now, relating this to 5.1 then, if we want to evaluate this integral using the midpoint rule. So I didn't use a midpoint rule on any of the previous examples, so that's why I chose it this time. So sine of square root of x. Okay. If we graph that, so let me do x. What that's going to do, that's just going to kind of take the sine curve and it's going to elongate it. And it's going to look like that. Okay. Now, we want to go from 0 to 8. So 8 would be like maybe somewhere up in here. Okay, it's before it crosses that x-axis. And we want 4 intervals. So 2, 4, so that's 4 intervals. So our delta x is going to be 8 minus 0 over 4. So the length of each of those intervals is going to be 2. Okay. Now the midpoint means we're going to go right smack dab in the middle of those things. So in between 1 and 2 is, or 0 and 2, halfway is 1. Halfway between 2 and 4 is 3, 5, and 7. And that's where we want to evaluate our functions. So our little boxes are going to look like, so. So each of those rectangles, all I'm doing is adding those things up, right? The areas for each of them. So for the first one, take the base times the height, which would be f of 1, plus, now I'm going to write it in, well, I'll do that in a second, plus 2f of 3 plus 2 times f of 5 plus 2 times f of 7. Yeah, put some extra parentheses in there. That's all right. Now you can factor out that 2 if you would like. Of course, you don't have to, but I'm going to just because. Now, f of 1, I'm just going to go ahead and use my calculator to evaluate those things. Okay, so when it's 1, we're about 0.84. And f of 3 is about 0.98. Well, let's go with 99. It's actually round correctly there. Evaluate the function at 5. We get 0.79. And at 7, 0.48. Now adding those things up. 6.1. So area is about 6.2. So that's our approximation. Now, we could use the calculator to get a little bit better one, right? So if I use the from 0 to 8, from the calculator, the area turns out to be 5.998, which really isn't too far off that midpoint rule, is it? In fact, when we talk about the other things, the midpoint rule usually gives a better estimate than the left endpoint or the right endpoint. So to do this on your calculator, by the way, you just want to put in y1 your function, okay, and then graph that sucker. Now next you would do second trace. That's your calc menu. And then you'll see down on option number 7, I'm using the TI-84. So option 7, what you'll see is this symbol. Click that, and then you put in lower limit or lower bound. Then you put in your upper bound. And then you hit enter, and the answer pops up down at the bottom. So, and it even kind of draws in the graph what your area is you're finding. So there's using the midpoint rule to estimate our integral. So notice it's nothing really any different. So let's use our definition to evaluate this integral, and we need to be careful about this, okay? So our definition says we want limit as n approaches infinity. The sum of I equals 1 to n of 4 minus 2 x of I delta x. So we need a couple of things in order to do this. First, what's delta x? So delta x is always the right endpoint minus the left endpoint over n. Okay, we don't know what our n is. I mean, that's the one that's going to infinity, right? So that's going to be 3 over n. So we know delta x is going to be that. Now we got to figure out what the x of i's are going to be. What are our sample points? Now think about our number line and our graph of this thing. Okay, so the graph of this function looks something like that. I didn't give myself enough room. I'm going to draw a little steeper. Okay, so the x-intercept of this graph is at 2, and we want to go all the way over here to 5. So we're counting by 3 over n's, right? So each little rectangle is going to have this base where we're counting our delta x's are 3 over n, okay? And we're going to go over and over and over. So we start at 2, and then we go 3 over n, okay? So this part would be 2 plus 3 over n. The next one would be 2 plus 2 times that, right? Okay, and all the way over until we get to 5. So first off, I'm going to use right endpoints. Right endpoints. And there's probably a couple of ways that you could go about doing this. So I think the easiest is we start at 2, and then we go over 1 of the 3 over n's, then we go over 2 of the 3 over n's, and we work our way down the list that way, right? So each of these endpoints, okay, so we'll have our 2 plus 3i over n. Now the I is just, remember, just which interval we're in. So if we're in the first interval, that just means that's this one. In the second interval, we're evaluating our height of our rectangle at this point. We've moved 2 intervals over. Okay? So this is what the x sub I is going to be. So I'm going to make 2 substitutions. This one and the delta x being 3 over n. So that's going to equal the limit as n approaches infinity, sum of I equals 1 to n, 4 minus 2 times, 2 plus 3i over n times delta x. Okay. So that would just be 3 over n. Now I'm going to factor out the 3 over n. So I'm going to take a lot of little steps here, because the algebra, I don't want you getting too tied up in it. So we're just going to factor out the 3 over n. Okay. And I'm going to go ahead and distribute this negative 2. All right, because we'll get the 4 here, that will get the 6. Okay. Now notice those 4s are going to give me a 0. That's nice. So all we're left with is negative 6i over n. Now, the I is the only variable in this sum, okay? Because the I is changing as far as the sum is concerned. The n is staying fixed. We won't deal with n until we actually do the limit. Okay, so we've got to think about like an order of operations type thing. So what that means is I can factor out the negative 6 over n. And that's going to give me negative 18 over n squared times the sum of I equals 1 to n of I. Now what? So this piece right here, okay, there's some formulas in the book, and we're going to get to these more later, but just kind of take my word for it. This is n times n plus 1 over 2. So I'm going to substitute in that formula to figure out what that sum is. Now, going back to our limit rules and stuff like that, well, let me make it a little bit more obvious. If I multiply this stuff out, we get negative 18n squared minus 18n over 2n squared. Now, we can look at L'Hopital's rule, because that's an infinity over infinity type thing. Okay, but remember, with polynomials, we ignored this stuff, right, because that didn't contribute much. When you start talking about things going to infinity, the n squareds cancel out, and then you get negative 18 over 2. So this limit would equal negative 18 over 2, which would equal negative 9. So the area is negative 9. Now that makes sense, and I don't think I mentioned it earlier, but when we talk about this area, if it's underneath of the x-axis, it's going to be a negative area. Okay? Now we could actually verify this really easily. If we look at our triangle that we've made, okay, that's just this triangle that's under here, right? And that's the point 2, 0. And here, if we go over to 5, so that's the point 5, 0, and down here would be the point 5, negative 6. How do you find the area of a triangle? Because that's what we're asking about, right? It's 1/2 base times height. So 1/2, and the base is from 2 to 5, so that's 3. The height is from here down, so that would be 6. And if we multiply that out, we get a 9, and since it's under the axis, that'll be the negative 9. So that kind of verifies what we've got there. So you can do this stuff geometrically if you have formulas for the areas and stuff like that. Now, a couple rules for integrals and stuff. You can always split areas up, and that's what number 2 and number 4 are saying. If you have a sum of things, you can always do the integral of each piece and then add them up. The area of a constant, well, it's just the difference of the endpoints times the constant, because think about a constant, if I graph that, that would look something like this. And if we're between A and B, and the constant up here, the y-coordinate C, and I want this area, well, what's the base times the height? The base is B minus A. The height of that sucker is C. So that's all number 1 is. And number 3 says that if you have a constant multiple times your function, you could always factor that out of your integrand. So one last one, and this is strictly kind of a geometric interpretation of this, using those properties. Say, okay, well, let's find the integral from g of x from 0 to 7. So what I'm finding then is all of this area, right? So if we look at just the first part, we go and we have this big old tall triangle. So that's 1/2. What's the base of this triangle? I'm just looking from 0 to 2, right? So the base is 2, the height is 4. Okay. Now I'm looking at this half circle piece. So what's the area for circle is pi r squared, right? So we'll have pi times the radius for that. Well, here's the midpoint. The radius is 2. And we only have half a circle, so I'm going to divide that by 2. And then we're going to have this little triangle out here at the end. Its base is 1 and its height is 1. So my area then is 4 plus 2 pi plus 1/2. Well, that's 5/2 plus 2 pi would be my area. So you can do this stuff if you have a formula for your geometric shape, if the function makes a particular shape. Otherwise, for right now, we're limited to using those Riemann sums to approximate it, or maybe using the limit definition to actually find it. In the next section, we're going to get into much easier ways to evaluate these things using our fundamental theorem of calculus. So, good luck. Let me know if you have any questions, because I'm sure we're getting into sections where you guys are going to start having some questions more than those last couple sections. This is a little bit more difficult, so please be proactive and ask away, okay?